Lesson 2.1, Newton's Laws of Motion. We have been studying kinematics. Kinematics is about how things move and describing their motion. This new unit is about dynamics, which is why things move, what causes motion or change in motion. To do that, we need to discuss forces. A force is a push or a pull. I know it sounds very scientific, doesn't it? It's a push or a pull. It is a vector, meaning it has direction. The unit of a force is a Newton, named after Isaac Newton. We measure it with a spring scale. When we solve force problems, we often need to draw what are called free body diagrams, which is a picture of an object with all the forces acting on this object. For example, this little weight that's hanging here has the force of weight down, the force of tension in the string going up. Do part 1 of your Newton Laws lab right now. Pause the video until you're done. Newton's first law of motion is, a body at rest remains at rest, or, if in motion, remains in motion at a constant velocity, unless acted on by a net external force. This is often called the law of inertia. Inertia is the property of objects to remain in constant motion or rest. Mass is the measure of inertia. Pause this video and do part 2 of your Newton Laws lab. Newton's second law of motion is, acceleration of a system is directly proportional to and in the same direction as the net force acting on the system, and inversely proportional to its mass, which is often written as F equals ma, or net force equals mass times acceleration. Net force is the vector sum, so we're adding all the vectors. Remember, if they're going different directions, you have to find the components to get the resultant. Pause the video and do part 3 of the Newton Laws lab. Newton's third law of motion is, whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that exerts it. In other words, every force has an equal and opposite reaction force. For example, you're sitting in your chair, so you're pushing down on your chair. The chair is pushing back on you, otherwise you'd just fall straight through the chair. That size of the force between you and the chair and you are the same size, in this case equal to your weight, and opposite directions. You're pushing down, the chair is pushing up. A football player named Al is blocking a player on the other team named Bob. Al applies 1,500 newtons of force on Bob. If Bob's mass is 100 kilograms, what is his acceleration? Well, if we have F equals ma, our force is 1,500 newtons, and Bob's mass is 100 kilograms. Just divide by the 100, and our acceleration is 15 meters per second squared, which actually turns out to be a very large acceleration. What would be the size of the force on Al? Well, from Newton's third law, for every force, there's an equal and opposite reaction force, so it's going to be the same size force, but the opposite direction. So the size is 1,500 newtons, and the direction is the opposite direction. If Al's mass was 75 kilograms, what would be his acceleration? Well, again, we can go F equals ma, Newton's second law. The force was 1,500 newtons. The mass is 75 kilograms. Divide and you get negative 20 meters per second, which means he's going backwards at 20 meters per second squared for his acceleration. A golf ball hit by a driver can accelerate from rest to 67 meters per second in 1 millisecond while the driver is in contact with the ball. How much average force does the golf ball experience? Well, if I'm going to use F equals ma, I'm looking for the force, but I don't have the acceleration. So first of all, I need to find the acceleration. We know our initial velocity is 0 because it says from rest. We know our final velocity is 67 meters per second. We know our time is 1 millisecond, so it's 1 times 10 to the negative 3 seconds. And I want acceleration. So I could probably use v equals at plus v0. So it looks like I just need to divide by the 1 times 10 to the negative 3. And so we end up with 67,000 meters per second squared. So our force is our mass times our acceleration, which gives us 3,082 newtons. Of course, that's too many significant figures. There's actually just one significant figure, so that'd be about 3,000 newtons.